Hello everyone, I am Himanshu Vasnani. I am from Department of Mechanical Engineering. So today we are discussing on the subject non-destructive evaluation and testing. The subject code is ME419, week number 2, lecture number 10 in the series. And today's topics are radiographic testing, sources of attenuation, radio isotopes, gamma ray sources, and radiographic film. Today's objective is to provide students with a basic understanding of radiographic testing, sources of attenuation, radio isotopes, gamma ray sources, to know about radiographic film selection, packaging and handling. And today's outcome will be students will have an understanding of radiographic testing, sources of attenuation, radio isotopes, gamma ray sources. Students will understand the various factors influencing radiographic film selection, packaging and handling. So let us start today's lecture. Uh, this- uh, so let's start with today's lecture. So the attenuation that results. Now the topic is sources of attenuation. So let's start with today's thing. Attenuation that results due to the interaction between penetrating radiation and the matter is not a simple process. Okay. The interaction between penetrating radiation and matter is not a simple process in radiography. Okay. A single interaction event between a primary X-ray photon and a particle of matter does not usually result in a photon changing to some other form of energy and effectively disappearing. Several interaction events are usually involved, and the total attenuation is the sum of the attenuation due to different type of interactions. These interactions include the photoelectric effect, scattering, and pair protection. Okay. So now what happens that there are different kinds of interaction happening during the process. So now we will discuss the different kinds of interactions like photoelectric effect, scattering, and pair protection in detail to understand the sources of attenuation. Now photoelectric absorption of X-rays occurs when X-ray photon is absorbed. I repeat once again. Photoelectric absorption of X-rays occurs when X-ray photon is absorbed, resulting in the ejection of electrons from the outer shell of the atom and hence the ionization of the atom. Subsequently, the ionized atom returns to the neutral state with the emission of X-ray characteristic of the atom. Okay. Now this you can see in the diagram there's an incident photon and how this works. Okay, this subsequent emission of low is generally absorbed and does not contribute to or hinder the image making process. Okay, the image that is obtained after radiography. Photoelectron absorption is the dominant process for X-ray absorption up to energies of 500 kilojoule. Okay, photoelectric absorption is also dominant for atoms of high atomic numbers. So you, after understanding this, you know that photoelectric absorption of X-ray is so much important. Okay, here the when the X-rays photon is absorbed, that what happens that result into the ejection of electrons from the outer shell of the atom and hence the ionization of the atom takes place. Okay, so photoelectric absorption is also important. Then Crompton scattering. Then this occurs when incident X-ray photon is deflected from its original path by an interaction with an electron. Okay, this occurs when the incident X-ray photon is deflected from its original path by an interaction with an electron. So the electron gains energy and is ejected from its orbital position. Okay, the X-ray photon loses energy due to the interaction. I repeat, the X-ray photon loses energy due to interaction but continues to travel through the material along an altered path. Okay, then since the scattered X-ray photon has less energy due to traveling, therefore has a longer wavelength than the incident photon. Okay, so this is how Crompton scattering takes. I repeat once again. This occurs when an incident X-ray photon is deflected from its original path by interaction with an electron. Okay, this is Compton scattering. It is noted by capital C. Now, pair production. It is noted by capital P. Now, this is a very important term when we talk about attention of process of attenuation. So, the interaction, one more in we discuss about pair production now in detail. Now, pair production can occur when the X-ray photon energy is greater than 1.02 MeV, but really only becomes significant at energy around 10 MeV. So you can say that there is a big difference, okay, between the two energy. Now, pair production occurs when an electron and positron are created with annihilation of the X-ray photon. So positrons are very short-lived and disappear like positron annihilation with the formation of two photons of 0.51 MeV energy. Pair production is of a particular importance when high energy photons pass through materials of high atomic number. So in this way, pair production is helpful, is useful. Okay, it has importance when high energy photons pass through materials of high atomic number. Okay. So now we are discussing about equipments and materials used in radiographic testing. So the first one is X-ray generators. You know that these are also important to study about the different equipments and materials that we use for radiographic testing. Okay, now we will discuss each of them in detail one by one. X-ray generators. Okay, the you can see in the right hand side the diagram displaying all the components. Okay, this is also helpful. Like there is a high voltage power supply, then there is a low voltage power supply, then a cathode structure, focusing curve, then you have a target on which you have a focal spot, you have an anode structure like a cathode structure, you have an anode structure, then there's an electron beam from the filament, then you have tube envelope, then you have an X-ray beam. So this whole diagram is displayed in front of you. So the major components of X-ray generators are the tube, the high voltage generator, and the control console and the cooling system. I repeat, the major components of an X-ray generator are the tube, the high voltage generator, the control console, and the cooling system. Now, X-rays are generated by directing a stream of high-speed electrons. You can see in the diagram by directing a stream of high-speed electrons at a target material such as tungsten, which has high atomic number. Okay, when the electrons are slowed or stopped by the interaction of atomic particles of the target, X radiations is produced. So this is accomplished in an X-ray tube such as one shown in the figure. Okay, I repeat once again. X-rays are generated by directing a stream of high speed electrons at a target material such as tungsten, just high atomic number. So when the electrons are slowed or stopped by the interaction with the atomic particles of the target, X radiation is produced. This is accomplished in the X-ray tube and such as one shown in this, you can see here. Now The tube cathode, the filament, is heated with a low voltage current of a few amperes. The filament heats up and the electrons in the wire become loosely held. The filament heats up and the electrons in the wire become loosely held. A large electrical potential is created between the cathode and the anode by the high voltage generator. Okay, by the high voltage generator, you can see that our potential is held. Then electrons that break free of the cathode are strongly attracted to the anode target. So the stream of electrons between the cathode and the anode is the tube current. Is the tube current. The tube current is measured in milliamperes and is controlled by regulating the low voltage heating current applied to the cathode. I repeat once again, to understand, the tube current is measured in milliamperes and is controlled by regulating the low voltage heating current applied to the cathode. The higher the temperature of the filament, you can see in the diagram, temperature of the filament, the larger the number of electrons that leave the cathode and travel to the anode. You can see the filament in the right hand side in the diagram. The higher the temperature of the filament, the larger the number of electrons that leave the cathode and travel to the anode. So the milliampere or the current setting on the control console regulates the filament temperature, which relates the intensity of the X-ray output. Okay, which relates to the intensity of the X-ray output. So the high voltage between the cathode and the anode, you can see in the diagram, affects the speed at which the electron and strike the anode. Okay, the cathode is on the left hand side, anode is on the right hand side. The diagram. The higher the kilovoltage, the more speed and therefore energy the electrons have when they strike the anode. Electrons striking with more energy, okay, with more energy when the electrons strike, resulting in X-ray with more penetrating power. I repeat once again, energy in her electrons striking with more energy result in X-rays with more penetrating power. The high voltage potential measured in kilovolts, and this is controlled with the voltage or kilovoltage control on the control console. Okay, this is controlled with the help on the control console. An increase in the kilovoltage will also result in an increase in the intensity of the radiation. Okay, I repeat once again, it is very good thing. Electrons striking with more energy result in X-ray with more penetrating power. And the high voltage potential is measured in kilovolts, and this is controlled with the help of voltage or kilovoltage control on the control console for animals. Okay, an increase in the kilovoltage will also result in increase in the intensity of the radiation. So this is how you control the, you can say, flow of it. Okay, then you can see in the right hand side diagram also there is a graph between wavelength and intensity. So you can say when the high voltage is graph is shown and low voltage graph is shown. Okay. Then the bottom there is high current and low current graph is shown. Now the figure shows the spectrum of the radiated X-ray associated with the voltage and current setting. The upper diagram is showing voltage settings and in the bottom diagram it is showing current settings denoted by A and B. The top figure shows that the increasing the kV increases both the energy of X-rays and also increases the intensity of the radiation. I repeat, the top figure shows that the increasing the kV increases both the energies of X-rays and also increase the intensity of radiation, number of photons. Increase in the current, on the other hand, also increase the intensity without shifting the spectrum. Okay, here the spectrum is not shifting. Okay, but okay. Now a focusing cup. You have seen a term called as focal spot in the previous diagram. Let me show you once again. Focal cup. You can see in this diagram at the target there is a term called focal cup is shown in this diagram. Now we'll discuss about this term. Okay, we'll discuss about this term. Let me get to the respective slide. Okay, yeah, right. A focusing cup is used to concentrate the stream of electrons to a small area of the target called the focal spot. Okay, concentrate the stream of electrons to a small area of the target. It's called focal spot. The focus spot size is an important factor in system ability to produce a sharp image. Obviously, it is an important factor because okay, then much of the energy applied to the tube is transformed into heat at the focal spot of the anode. On the right hand side, you can feel no? So the anode target is commonly made from tungsten. Why tungsten? Because of its property that it has high melting point in addition to a high atomic number. That's why we go with tungsten. Okay, I repeat once again, and you should understand this also. The anode target, okay, is commonly made from tungsten because of its property that it has high melting point in addition to a high atomic number. However, cooling of the anode by active or passive means is necessary. So, either water or oil recirculating systems are often used to cool the tubes. Understand? Like some low power tubes are cooled simply with the use of thermally conductive materials and heat radiating film. Okay, like some we go with that because cooling is also important. So in order to prevent the cathode from burning up and to prevent arcing between the anode and the cathode, all of the oxygen is removed from the tube by pulling a vacuum. So some systems have external vacuum pumps to remove any oxygen that may have leaked into the tube. So there are arrangements for proper functioning of the Xray generators. There are some arrangements that is helpful in removing the oxygen from the tube. Okay, the purpose is to prevent the cathode from burning. The purpose is to prevent arcing between the anode and the cathode. Okay, so next. However, most industrial X-ray tubes simply require a warm-up procedure to be followed. Okay, this warm-up procedure carefully raises the tube current and voltage to slow down any of the available oxygen before the tube is operated at high power. Okay, you can understand the warm-up procedure carefully raises the tube current and voltage to slowly burn down the available oxygen before the tube is operated at high power. Or you can take that it can be executed with the vacuum. You can say taken out also. In addition, X-ray generators usually have a filter along a beam bar placed at or near the X-ray port. The filters consist of a thin sheet of material, often high atomic number material such as lead, copper, or brass, placed in the useful beam to modify the spatial distribution of the beam. Okay, there are also filters. Okay, that help. That is helpful to place in the useful beam to modify the spatial distribution. The filtration is required Now listen carefully. This is also important. That filtration is required to absorb the lower energy X-ray photons emitted by the tube before they reach the target. Why we are doing this? We are doing this? In order to produce a cleaner image, since the lower energy X-ray photons tend to scatter. We have studied this in earlier also that scattering is occurring. So what we do, we try to avoid the lower energy X-ray photons because they scatter. So what we do with the filtration. Okay, it absorbs the lower energy X-ray photons emitted by the tube before they reach the target in order to produce a cleaner image. Okay, now the other important component of an X-ray generating system is the control console. You can see in the diagram how a control console look like. Now consoles typically have a key lock to prevent unauthorized use of the system. Obviously, we need to have a, you can say, controlled usage of the control console. We need to take care. So we use have a key lock to prevent unauthorized use of the system. Now they will have a button to start the generation of X-rays and a button to manually stop the generation of X-rays. The three main adjustable controls you can see in the diagram also regulates the tube voltage in kilovolts, the tube amperage in milliamperes, and the exposure time in minutes and seconds. So some systems also have a switch to change the focal spot size of the tube also. This is the advanced feature. So they also have a switch to change the focal spot size of the tube. Focal spot I have discussed in the previous slides only. Okay. So we have a switch to change the focal spot size of the tube. Focal spot size, very good. Then radioisotope gamma ray sources. This is an also important topic in radiograph about the sources. Now we know that man-made radioactive sources are produced by introducing an extra neutron to atoms of the source material. I repeat, man-made radioactive sources are produced by introducing an extra neutron to atoms of the source material. Now, as the material gets rid of the neutron, okay, energy is released in the form of gamma rays. So, two of the most common industrial gamma ray sources for industrial radiography are iridium 192 and cobalt 60. In comparison to an X-ray generator, cobalt 60 produces energies comparable to a 1.25 MV X-ray system and iridium 192 to a 460 MV X-ray system. You can see the difference. Okay, how much energy they can produce, how much cobalt 60 is capable, and how much iridium 192 is capable. These high energies make it possible to penetrate thick material with relatively short exposure time. Okay, the energies that are produced by them, it's making them possible to penetrate thick materials with relatively short exposure time. This and the fact that sources are very portable are the main reason that gamma sources are widely used for field radiography. Because of the portability of these sources, it has made them widely used for field radiography. The gamma sources. Okay, this is the main reason that gamma sources are widely used for field radiography. Of course, the disadvantage of radioactive source is that it can never be turned off and safely manage the source is a constant responsibility. So we have an advantage, but we have disadvantages also. So we have to manage. Okay, we have to manage. We have to manage the source. We have to safely manage the source. That is important. Now you can see in the diagram how this radioactive isotope material is, how it is arranged. See in the diagram very easily. Now, physical size of an isotope material varies between manufacturers, but generally, an isotope material is a pellet that measures 1.5 mm into 1.5 mm. Okay, depending on the level of activity desired, a pellet, a pellet or pellets are loaded into a stainless steel capsule and sealed by welding. This capsule attached to short flexible cable. This capsule is attached to a small cable called as stick. See, we have to go with the standardization. So what they do, they generally make isotope material in a pallet size, and depending upon the usage or activity desired, a pallet or pellets these are loaded into a stainless steel capsule and sealed by welding. Okay, and then you attach that capsule to short flexible cable called as pigtail. Okay, the source capsule and the pigtail are housed in a shielding device referred to as a exposure device or camera. Referred to as exposure device or a camera. Depleted uranium is often used as shielding material for sources. See, shielding material is also important. Okay, so we have to use to have a shielding material. So depleted uranium, we can use it as a shielding material for sources. Okay, shielding material. The exposure device for Ind-192 and cobalt 60 sources will contain around 22 kg and 225 kg of shielding material. You can understand how much shielding material is required. Now, cobalt cameras are often fixed to a trailer and transported to and from the inspection sites. Okay, when the source is not being used to make an exposure, it is locked inside a exposure device. For safety reasons, for proper management reasons, for efficient reasons, when the source is not being used to make an exposure, it is locked inside the exposure device. Okay, it is for safety reasons. To make a radiographic exposure, a crank-out mechanism and a guided tube are attached to opposite ends of the exposure device. Okay, the guide tube often has a collimator usually made of tungsten at the end to shield the radiation except in the direction necessary to make the exposure. Okay, the end of the guide tube is secured in the location where the radiation source needs to be produced a radiograph, which is important. Okay, which is important. You can see in the diagram how this arrangement is done. Okay, the crank out cable is stretched as far as possible to put as much distance as possible between the exposure device and the radiograph. To make the exposure, the radiographer quickly cranks the source out of the exposure device and into position in the collimator at the end of the guided tube. At the end of exposure time, the source is cranked back into the exposure device. Okay, this is for safety reasons. At the end of exposure time, the source is cranked back into the exposure device. This is a series of safety measures. There is a series of safety measures which include several radiation surveys that must be accomplished when making exposure with a gamma source. We have to be careful. We have to follow the instruction. We have to take care that proper the exposure device is safely handled. Okay, you can see in the diagram there is crank out, there is drive cable, there is the source, there is shielding, there is exposure device. So when it is stored, it is kept safely. Okay, when it's exposed in the exposure position, you can see the location. So we have to take care of the arrangement. Then radiographic film. Now X-ray films, the X-ray films are general radiography basically consists of an emulsion gelatin containing radiation sensitive silver halide crystals such as silver bromide or silver chloride. Okay. The emulsion is usually coated on both the sides of a flexible, transparent, blue tinted base in layers about 0.012 mm thick. To understand the sensitivity, the an adhesive undercoat fastens the emulsion to the film base and a very thin but tough coating covers the emulsion to protect it against the minor abrasion. The typical total thickness of the X-ray film is approximately 0.23 millimeters. You can see the total thickness of X-ray film. It is exactly 0.23 millimeters. Very minute. You can see in the diagram also there is a protective coating and then adhesive undercoat is there. Then there is a film base and after that the emulsion is there. So how they are trying to protect this film base? Okay. Though films are made to be sensitive for X-ray or gamma, yet they are also sensitive to visible light. Okay. So when X-rays, gamma rays or light strike the film, some of the halogen atoms are liberated from the silver halide crystal and thus leaving the silver atoms alone. Okay. So this change that halogen atoms are liberated from the silver halide crystal and silver atom is alone. This change is such a small nature that it cannot be detected by ordinary physical method and is called a hidden image. Latent image, you can call it a latent image. So when the film is exposed to a chemical solution or a developer, the reaction results in the formation of a black metallic silver. Now when we go with the film selection, what should we do? So selecting a proper film and developing a optimal radiographic technique for a particular component depends on a number of factors like composition, shape, and size of the part being examined. And in some cases, it's the weight and the location. Whether it is a location at a particular place or it is remotely located. So these factors should be considered. Then type of radiation used, whether X-rays from an X-ray generator or gamma rays from a radioactive source. What is the type of radiation you are using? Okay, that is also important. See, the shape is important, the size also important. Okay, weight is also important, but then the source type of radiation you are using that is also important. Then kilovolt is available with the X-ray equipment. Okay, or the intensity of the gamma radiation. This is also important. So these factors are important, and we should have a particular, we can say, values for them. Then relative importance of high radiographic detail for quick and economical results. Okay. Then film packaging. That was the film selection. Then comes the film packaging. Okay. So considering the factors that we just discussed above, we should select the film. Okay. Then we go with the next slide. Film packaging. Radiographic film can be purchased in a number of different packaging options and they are available in a variety of sizes. The most basic form is as individual sheets in a box for safety reasons also. In preparation for use, each sheet must be located into a cassette or a film holder in a dark room to protect it from exposure to light. This is all done for safety reasons to protect it. Industrial X-ray films are also available. Industrial X-ray films are also available in a form in which each sheet is enclosed in a light tight envelope. I repeat once again because this is a matter of concern. Industrial X-ray films are also available in a form in which each sheet is enclosed in a light tight envelope. The film can be exposed from either side without removing it from the protective packaging. A rip strip makes it easy to remove the film in the darkroom for processing. Packaged film, okay, packaged film is also available in the form of rolls, where that allows the radiographer to cut the film to any length. You can see the variety. Okay, in the roll also you have the packaged film, and you can the radiographer can has the flexibility to cut the film to any length. The ends of the packaging are sealed with electrical tape in the darkroom. The ends of the packaging are sealed with electrical tape in the darkroom. In application such as radiography of circumferential welds and the examination of long joint on an aircraft fuselage, long length of film offer great economic advantage. Okay, so this is film packaging. Now film handling. Okay, selection, then packaging, now handling. Very important. Now X-ray film produce should always be handled carefully to avoid physical strain such as pressure, squeezing, buckling, friction. So whenever films are loaded in semi-flexible holders or an external clamping devices are used, then care should be taken to be sure pressure is uniform. While clamping, the pressure is uniform. We should be careful with that for handling the films. Marks resulting from contact with fingers that are moist or contaminated with processing chemicals as well as crimp marks are avoided. I repeat, marks resulting from contact with fingers. Marks resulting from contact with fingers that are moist or contaminated with processing chemicals as well as crimp marks are avoided if large films are always grasped by the edges and allowed to hang free. Use of envelope packaged films avoid many of these problems until the envelope is opened for processing. Handle the film carefully. Proper pressure is applied for proper handling. Touching through fingers is also done in careful manner. Okay. Now radiographic consideration and techniques. These are small consideration, but we should also discuss with them also. Radiographic sensitivity. Okay. The usual objective in radiography is to produce an image showing the highest amount of detail possible. Okay. See, in liquid penetrant testing, we were concerned that it should be able to display information on the surface only, related to surface only. But when we talk about radiographic testing, we are getting to the interior of the material. So the objective in radiography is to produce an image showing the highest amount of detail possible of the workpiece. So this requires careful control of a number of different variables that can affect the image quality. Now radiographic sensitivity is a measure of the quality of an image in terms of smallest detail or discontinuity that may be detected. Listen carefully, I will repeat. Radiographic sensitivity is a measure of the quality of an image in terms of the smallest detail or discontinuity that may be detected. Radiographic sensitivity is dependent on the contrast and the definition of the image. Okay, it has these factors also, and it depends on the contrast and the definition of the image. Okay, like what is radiographic contrast? Now we will discuss. Radiographic contrast is the degree of density that two areas on a radiograph. Contrast makes it easier to distinguish features of interest such as defects from the surrounding area. The image to the right you can see shows two radiographs of the same step image. The upper radiograph has a high level of contrast you can see, and the lower radiograph has a lower level of contrast. While they are both imaging the same change, in high contrast image uses a larger change in radiographic density to show this change. In each of the two radiographs, there is a small dot. You can see in the center image. There is a small dot which is of equal density in both radiographs. It is much easier to see in the high contrast radiograph. So in this way, radiograph contrast is of importance. Okay. So now we will discuss with the MCQs. Okay, for today's lecture. So I'll go with the MCQs. So in radiographic testing, it happens when the incident X-ray photon is deflected from its original path by interaction with an electron. The electrons gain energy and is ejected from its orbital path. What do we call this? Either we call it as alpha particle or photoelectric particle absorption or Compton scattering or pair production. We have discussed this in our PPTs just when we were studying. It is called as a Compton scattering. Called as a Compton scattering, noted by C, capital C. You can see, okay, option also it is noted by capital C. In radiographic testing, when an atom undergoes in radiographic testing, when an atom undergoes radioactive decay, its emission frequently follows beta decay, alpha decay, and other nuclear decay processes. What do we call it? It is called as gamma. Okay. In radiographic testing, when an atom undergoes radioactive decay, the emission of dash does not alter the number of photons or neutrons in the nucleus, but instead has the effect of moving the nucleus from a higher to a lower energy state. What do we call it? We call it as gamma. Okay. Then in radiography, it is the amount of energy passing through a given area that is perpendicular to the direction of radiation at a given unit of time. What do we call it? We call it as radiation intensity. Okay. Now, in radiographic testing, when an atom undergoes radioactive decay, these particles have a negative charge and are emitted by a specific radionuclide that will that will range in the energy. I repeat, that will range in energy from zero near up to a maximum value, which is characteristic of a particular transformation. What do we call it? We call it as beta particles. Now, in general, it is a method of inspecting materials for hidden flaws by using its ability of short wavelength electromagnetic radiation, high energy photons to penetrate various metals. What do we call it? Call it as radiographic testing. Sure. In radiographic testing, the process of X-ray occurs when the X-ray photon is absorbed, resulting in the ejection of electrons from outer shell of the atom, and hence the ionization of the atom. Subsequently, the ionized atom returns to the neutral state with the emission of an X-ray characteristic of an atom. What do we call it? Photoelectric absorption. Okay. Two of the most common industrial gamma ray sources for industrial radiography are iridium-192 and cobalt that we have just discussed in the previous slides. Now, in radiography, a focusing cup is used to concentrate the stream of electrons to a spot area of the target called the focus spot. I've shown you this in the diagram also, focus spot. So I repeat once again and you understand the question. In radiography, a focusing cup is used to concentrate the stream of electrons to a small area of the target called focus spot. True or false? True. Then next question. Oh, sorry. Uh, in radiography testing, the major components of an X-ray generator are tube, high voltage generator, control console, cooling system, or all of this. The answer is all of these E. So today we have completed our lecture and I hope you have understood what our motive of the lecture was. You can use these references, you can refer these references because they will provide you a broader knowledge of the special topics that we have studied and these will help you to increase your knowledge in the topics. You can find these books very easily in the library, okay? And I just want to say one thing that read books, okay? Try to understand the language because when you understand the language, then you will feel what you are reading and you will understand better what you are reading. Mere reading is not important. Understanding what you are reading is also important. Okay, so with a fresh mind, try to refer, try to read these references, which will help you to enhance your knowledge. Okay, so this is all for now. Thank you.